Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we will derive a 100% times 1 minus alpha prediction interval for y when x equals x star. Okay, so for instance, if alpha was 5%, we're going to be deriving 100 times 1 minus 5%, right? So a 95% confidence interval. Okay, so before we talk about this derivation, let's talk about the ingredients we will need to do it. Okay, so the first ingredient will be the model that we're going to be considering. So in this derivation here, we're going to consider the following model. Yi, our response variable, will be beta 0 plus beta 1 times xi minus x bar plus a random fluctuation, our epsilon I, relative to that ith observation. Okay, so as I said, what we're doing here is we are considering the centered model, right? Centered model. In your textbook, they refer to the classical regression model. Okay, but I think the derivation using this centered model is easier, and you can take a look at our textbook and you'll see it will be similar to what we're going to be doing here together. Okay, so now let me remind you what our assumptions about the error are. We are assuming that the random fluctuation epsilon I has a normal distribution with mean 0 and variance sigma square. There we are. That sigma square is the same regardless of the value of the predictor variable xi, okay? And we are assuming that the epsilon i's are independent. Okay? Okay. Epsilon i's are independent. Okay. So, these assumptions about the error have some consequences for the distribution of the y's, right? The y's will be normally distributed, right? And the mean of the response variable yi will be the expected value of this expression here. Beta 0 and beta 1 are our parameters, They are unknown constants, but constants. And these guys are given. So once we have this guy, xi, it's observed, it's constant. So the only random variable here in the expression that defines yi is epsilon. So the expected value of a constant, just a constant, expected value of epsilon I, 0. So this would be the expected value of our response variable. Okay, let's find the variance. In this case, variance of yi, variance of a constant, 0, right? And it will be independent of epsilon. And in that case, right, given our assumptions, the variance of yi will be just the variance of epsilon I, which is sigma squared. Okay. Okay. And we know that sigma square is the other parameter of interest, right? And now we know how to estimate it as well. Something that we are also going to need to be able to talk about this prediction are results that you have seen before. Okay, useful results that you have seen before. Useful results. Results for our derivation. Here we are. So first we need the estimator of beta 0, the y-intercept in our model, right? And since it's an estimator, we're going to be using that hat notation. We know that in this case, right, the estimator will be y bar. If you have the centered model, and that's why I wanted to start there, because if you had the other model, the classical model, this is going to be different. This estimator will be different. Okay. Okay. Now the other one that we have here is beta 1 hat. In that case, we know, right? We could show that the estimator for beta 1 will be given by the sum of the xi's minus x bar times yi. Okay, xi, let me see if I copy paste this, times our yi, right? This is I goes from 1 up to n, and then we would have the summation of the xi's minus x bar squared. I goes from 1 to n, right? Another way of rewriting this, and remember we showed this when we talked about the properties of the when we talked about the distribution of beta 1 hat, right? We can show that another way of expressing beta 1 hat would be this, right? Instead of a yi, we're going to have the difference between yi minus y bar, right? And another way of remembering this would be just sxy, right? That's a notation that you have seen in your textbook. divided by SXX. So those expressions are equivalent. Okay. So anyway, why are we mentioning these? Because it will be useful to remember the properties, statistical properties of these guys. So the expected value of beta hat 0, right? It turns out we can easily show that the expected value of beta hat 0 happens to be beta 0. Okay? We can also show, right, that the variance of beta hat 0 is just sigma square divided by n, which, you know, if you want, we could quickly show that, right? Remember that the estimator is y bar, so y bar is the same as the sum of those y's divided by n, right? We know that these y's are independent, right? So since they are independent, the variance of a sum is the sum of variances. And something that we could also do before we use that result, that property of the variance, is factoring out that 1 over n. We know that when we do that, then we have to square that constant, and then, as I said, we would have the variance of a sum, right? And since they are independent, it's just the sum of variances. And what we said is, hey, the variance of yi is just sigma square, remember? So what we end up having is n times sigma square divided by n square, right? N times sigma square divided by n square, and in the end what we have is just sigma square divided by n, right? Okay. So when we talked about the properties and the distribution of beta 1 hat, we showed that beta 1 hat was an unbiased estimator of beta 1. So let me just write that down. We have seen and we have done that before in detail. We also derived the variance of beta 1 hat, which, as you recall, is just sigma square divided by SXX. And again, we did that in detail together. Okay, so these are going to be useful results, things that we need to have, you know, fresh in our minds to, you know, derive that prediction interval that we are after. Okay, so our problem is predicting y star and y star given our model, right? Y star looks like this. It will be beta 0 plus beta 1 times x star minus x bar plus epsilon star. Okay, so it's response evaluated at a particular value x star. Okay, and of course this guy also, it's a random fluctuation particular to this observation of the response variable. Make sense? Okay, so we want to predict that guy. Epsilon star, okay, also that random fluctuation has a normal distribution, same variance, and it will be independent of the other epsilons that we have observed. Okay, but just let me remind you that this guy will have the same distribution, same parameters, epsilon star. Okay, okay. Now it makes sense, right, that if we want to estimate this quantity, we also talked about how in this case the maximum likelihood estimators of beta 0 and beta 1 happen to be the same as the least squares estimators, which are these guys. Okay, so one way of arguing that a good estimator for y star would be beta hat 0 plus beta hat 1, right, times x star minus x bar, would be using maximum likelihood by the invariance property of maximum likelihood. Okay, so our point estimate will be just y star hat will be beta hat 0 plus beta hat 1 times x star minus x bar. Okay? Okay. Now, let's rewrite y star. Yeah. Note that y star, let me borrow this from here, y star is the same as y hat star plus y star minus, I need a star here as well, right? Okay. Make sense? Y star, the observation, is the same as a prediction plus a prediction error, right? Prediction plus prediction error, or just error. Okay? Okay. So, it will be important for us to study this prediction error, the statistical properties of that prediction error. Studying those properties will allow us to derive the prediction interval that we want. Okay, so now let's talk in more detail about this guy, the prediction error, right? Okay, so it's this guy, right? Y star minus y hat star. So let's just, expand what the difference is. Y star is given by that expression in terms of our parameters and that random fluctuation epsilon star minus, and then we have this guy here, right? So note that this would be a minus sign here. You guys agree? Okay, now let's re-express this. Okay, let's find the terms that are similar, right? And let's rewrite this line that we have here. Okay, so first this one, epsilon star, let's place it here. Now let's see which terms have to do with beta 0, right? This guy here, this guy here, beta hat 0, then these two terms have a common factor, right? X star minus X bar. So let's rewrite those together. So it would be beta 1 minus beta 1 hat. Times this is a common factor, right? Okay, so now we said that we need to study the statistical properties of that prediction error. Okay, so let us start with the part of the prediction error, with one of the terms that define the prediction error, right? With y hat star. Okay, so let's find the expected value of y hat star. So y hat star, right, is this guy here, right? So let's find the expected value of that expression beta hat 0 plus beta hat 1 times x star minus x bar. Let's find the expected value of that expression. That's expected value of a sum. So that's the same as the sum of expected values. Let me copy paste this. X star will be, a constant, right? So we are going to be factoring that out. Then we're going to use the useful results that we know, right? So expected value of beta hat 0. We know that it's an beta hat 0 is an unbiased estimator of beta hat 0 has as its expected value beta 0, right? Okay, so again we know that beta hat 1 is an unbiased estimator of beta 1, right? So we just have beta 1 there, times this. So as we can see, our point estimator is an unbiased estimator of y. Well, yeah, it will be a good estimator of y star, right? Okay, so now let's find the variance of y hat star. Let me copy paste this. So now we have the variance of a sum, right? Now this is where using that centered model becomes very convenient, because if you have the variance of a sum, right, it will be the sum of variances, and then we will have the covariances to take into account, right? But we know that the covariance between beta 0 and beta beta hat 0 and beta hat 1 for the centered model, right? In that case, the covariance between them is 0. So we just have to compute the sum. Okay, no need to take into account the covariance term. So let me just write this down here, right? Variance of this, and let me just here remind you that recall that covariance between beta hat 0 and beta hat 1 is 0, right? Okay, that's why we were able to just re-express variance of that sum as the sum of variances. Okay, now let's use properties of variance. Variance of beta hat 0, remember we derived that one just a few minutes ago together, and that's sigma square divided by n. Now we have to square that constant, and then multiply by the variance of beta hat 1, which happens to be sigma squared divided by SXX. So let me just factor this guy out and square it, and then multiply by the variance of beta 1 hat, which is sigma square divided by SXX. Okay, great. So again, this is just part of the story, because we know that we want to study the prediction error, and this is just one term that defines the prediction error. Okay, now using what we just derived, we are going to find the expected value of the prediction error, right? Okay, so here we go. Now let's compute the expected value of y star minus y hat star. Okay, now let me remind you what we had. That difference we computed here, so let me copy and paste that expression. Okay, so again, expected value of a sum of expected values, right? So we're going to have expected value of epsilon star. We already know that is going to be in the end 0 by assumption, right? Now we are going to have the expected value of that difference, expected value of beta 0 minus beta hat 0, right? But we know that beta hat 0 is an unbiased estimator of beta 0, so that difference is going to be in the end 0 as well. And then we have a constant, right? X star minus x bar times expected value of beta 1 minus beta hat 1. We have the same situation for that guy, right? That beta 1 hat is an unbiased estimator of beta 1. So in the end, again, by assumption, expected value of epsilon star 0, expected value of that difference, beta 0 minus beta hat 0, is going to be 0. Expected value of beta 1 minus beta hat 1 is going to be 0 times x star minus x bar. That's going to be 0 in the end. Okay, so the expected value of our prediction error is 0. Okay, now let's find the variance. Okay, so for that variance, to find the variance, before we do that, let me remind you about a couple of things here. So recall that, and what we're going to be doing here is reminding ourselves about the expression that defines y hat star. Let me rewrite it here. Yeah. So recall that y hat star is defined like that, and also we are going to remind ourselves how y star is defined, right? So y star is just something similar to that, but with the unobserved error term, right? This guy here. So, what I want you to remember is that y hat star is constructed using the first n observations from your sample, y1, y2 up to yn, right? So in the case of beta hat 0, you know that it's y bar, your estimator, right? Okay. So that's again a linear combination of the first n observations, right? Equals sum of y I divided by n. I goes from 1 up to n, okay? And for beta hat 1, this is also a linear combination again of those first n observations that you had of the response variable. So this guy, y hat star, is a linear combination of the yi's, y1, y2 up to yn, but y star, right, is independent. It's another guy, is independent from that set of n y's that you had previously, right? So these guys are independent. Okay. So let's find the variance of the error of the error. Okay. Now we want the variance. So in that case, we have the variance of a sum, basically, right? You have something like this. It's the same as this. So variance of a sum, right? But if you have the variance of a sum and these terms are independent, it's just the sum of variances, right? So recall that y star and y hat star are independent. So since they are independent, the covariance between them is 0, and then the variance of a sum is just the sum of variances. So what we end up with is just this. Since the variance of -1 times y hat star, right, is going to be -1 square, then we just end up with the variance of y hat star. Okay. So now what we have been doing will be useful. Those useful results that we mentioned. Okay, so variance of y star. Oh, it's just the variance of that expression here, but we know that these are constants, right? So the only term that has an actual variance is epsilon star, and the variance of epsilon star is sigma square by assumption, right? Sigma square. Now we need the variance of y hat star, and we must have it somewhere here, right here. Okay, so let's just copy and paste that expression. Make sense? Now let's try and make it look a bit nicer. We're going to factor out that sigma square. So what we have here is just sigma square times, it's going to be 1 plus 1 over n, right? Plus, and then we will have x star minus x bar square divided by sxx. This guy here divided by sxx. Okay, so same thing. So now we have the variance of the prediction error. Okay. Okay. So now something that will be important to derive that prediction interval that we wanted from the start is remembering a definition of t-distribution. So a t-distribution, we know it's normal 0, 1 divided by the square root of a chi-square with, say, k degrees of freedom divided by its own k degrees of freedom. So that ratio, right, dividing that normal 0, 1 by the square root of that chi-square with k degrees of freedom divided by its own degrees of freedom k, would have a t-distribution with k degrees of freedom. Okay? Okay, so let's talk about the prediction error, right? Note that the prediction error, right, is a linear combination of normally distributed random variables, right? So it turns out that y star minus y hat star has a normal distribution, right? Just because of the assumptions that we made about the random fluctuations, about the epsilons, right? And the expected value of that guy, 0, variance of that guy, of our prediction error, this guy, sigma square times 1 plus 1 over n plus x star minus x bar square divided by sxx, right? Okay, so let's just say that note that prediction error, right? This guy, that difference, oh, let me fix that. Okay. Note that our prediction error has a normal distribution with mean 0 and variance this guy. Okay. Now, if we divide by the standard deviation, right, we end up with a normal 0, 1. So let me write that down, that x star minus x star hat divided by, now I will need the square root of this. Okay, so that ratio has a normal 0-1 distribution. So that would give us the first ingredient in that t-distribution that I mentioned, right? Okay, something else that you guys have seen and used before, right? Recalling that n, let me write it down like this, yeah, n minus 2 times s square divided by sigma square that has a chi-square distribution with n minus 2 degrees of freedom. Let me find a chi-square here. Chi. There we are. Chi-square with n minus 2 degrees of freedom. Okay, we know that. And where, let me remind you what s square represents, where s square equals just you know, the sum of squared residuals, yi minus yi hat squared. That guy has to be divided by n minus 2, right? Okay, so that's s square. And we know that that guy is an unbiased estimator of sigma square. Okay, so anyway, so this guy here divided by n minus 2 would be a good candidate for our t-distribution. Okay, so let me just say that this guy will be our numerator. Let me open another one. We're almost there. Let me copy and paste these guys. So this guy here will be our numerator, and this guy here will be our denominator. Okay, so let's do this. It would be kind of a big ratio. This guy here our numerator, sorry, we're going to be dividing by the square root. We need the square root, remember. We have to divide by the degrees of freedom of our chi-square, and our chi-square is this guy. right? Now note how that n minus 2 will cancel out with that n minus 2, how we are going to have the square root of s squared divided by sigma square, right? And I'm going to rewrite that sigma square like just I mean, since we have the square root of a product is the product of square roots, the square root of sigma square will be just sigma, right? So let me copy and paste this and try and simplify that. That's going to be just sigma. Oops. I want it here, right? Sigma. As we said, these cancel out. It's going to be square root of s squared divided by sigma square. That in the end will be just s divided by sigma. So let me just write that down. S divided by sigma. Make sense? One more step and we're there. These sigmas will cancel out and then we will have just y star minus y hat star divided by s divided by the square root of 1 plus 1 over n plus x star minus x bar squared divided by sxx. Make sense? So I'm just going to copy paste the numerator because that's what we are going to have basically in the end. Make sense? Because these sigmas will cancel out, then we do the math, and then it would be s times this, and then 1 times this, and then we have in the end this expression x star minus x hat star divided by s divided by that square root. Okay, and this guy has a t-distribution with n minus 2 degrees of freedom. Okay, makes sense? And then we can use this as a pivotal quantity, right? We just solve for y star, right? And what we're going to end up with is a critical value from a t-distribution with n minus 2 degrees of freedom times this plus minus our point estimate. Make sense? Okay, so let me show you what the expression of the prediction interval looks like from our lecture notes. Give me just a sec. Okay, I'm back. I found it. Okay, so see, this is our point estimate. That's y hat star plus minus a critical value from a t-distribution with n minus 2 degrees of freedom times s times the square root of 1 plus 1 over n plus x star minus x bar squared divided by s x x. Right? So we are done. Okay, so summarizing, what we did is we see why this expression makes sense. To derive that expression, what we had to do was to study the statistical properties of the prediction error, and in order to do that, well, we had to resort to use the knowledge that we had about the distribution and statistical properties of our estimators for beta hat 0, our estimators beta hat 0 and beta hat 1. Okay, make sense? And of course the estimator for sigma square as well, right? S square. Okay, well, that's it for now. Please keep working hard. Take care. Thanks for watching. See you next time. Bye.